Hi everyone, this is the third and final video in my series about proof, and today we're going to be looking at one final type of proof, which is proof by contradiction. So to start off and motivate what we're looking at today, I have started off with a quote from Alice in Wonderland, which you might be familiar with. And today's focus is going to be on contradictions. So contradictions can't exist in mathematics because they're kind of logically contradictory, almost by definition. Something can't be both true and not true at the same time. So if we discover one, chances are we've probably done something wrong, and that kind of is the idea behind a proof by contradiction. So if you get a statement of the form P implies Q, then the idea is you can prove that by assuming that the statement is false. And for the statement P implies Q to be false, we need to have Q being true and then Q being false. So that's our setup. We assume that P is true, but then that Q is false. From there, we make some logical deductions, we do some kind of argumentation, we make some calculations, we follow some steps, and then our idea is to show that P is false. But then if P is false, we've then got a contradiction because we assumed that P was true at the beginning. So because of that contradiction, our assumption that the statement was not true can't be right. So we've in fact proved the statement. Okay. Now, in a roundabout way, what we've done here is we've done what we call a proof by contrapositive. So we've said in a previous video that not Q implies not P. If we can show that, then that's the same as showing that P implies Q. Okay, a statement and its contrapositive are both logically equivalent. So we're really just showing the contrapositive here. But that's the structure to follow if you want to kind of get all the marks in an exam. Okay, make some notes then on this first slide, and I've got several examples here, some of which are incredibly famous in mathematics and are centuries and centuries old. So that's going to be a lot of fun. Okay, let's dive right in. Again, for all of these, if you want to try these first of all, and you're familiar with the proof, then you can write it down before I give the solution. Okay, so example one, we are proving all of these using the method of contradiction, that if n squared is even, then n is even as well. Okay, you'll notice that that's got the structure that we talked about. That's a P implies Q. Maybe we'll label these up with what those are going to represent. So this first part, the hypothesis, is what we're calling P. And then we're showing that that implies this part here, which is Q. Okay, so the proof is going to go like this, following the structure from the previous slide. So we're going to assume that this first part is true, that's n squared is even. But then this conclusion is going to be false. So n is odd, okay? We're negating that to say that n is odd. Right, so now we've got to do some maths and show that we've got a contradiction here. So then if n is odd, then that means that n is 2m plus 1. Okay, that's the definition of an odd number. But then if I square that, I'm going to get 2m plus 1 all squared. That's going to be 4m squared plus 4m plus 1. I can then use a factor of 2 to show that this is an odd number. So 2 times 2m squared plus 2m plus 1. That's n squared, but that's an odd number. Okay, but in our assumption step, we assume that n squared was even. So our contradiction is here because you can't have a number that's both even and odd. Okay, great, so that's done. Now, strictly speaking, we don't particularly need this assumption here that n squared is even because, as I said before, showing the contrapositive, just showing that n is odd implies that n squared is odd is enough to prove it. But in an exam, maybe write this down just to show that you're doing a proper proof by contradiction. Okay, I'll leave it to you as an exercise then to show the different statement here, that if n squared is odd, then n is odd. But I'll leave that to you because it's very similar and you can go through the same, pretty much the same argument there. Okay, example 2. Right, prove that if A, which is non-zero, is rational, and that B is irrational, then AB plus 1 is irrational. Okay, so we've got a couple of parts to the hypothesis for this question, right? So all of this is what we're kind of referring to as P, and then this part here is our conclusion. Okay, so the setup is going to be similar to how we had it before. We're going to assume that everything in red is true, but that the blue statement, which is the conclusion, is going to be false. Now, in order to do this, it's helpful to kind of have a good understanding of what we mean by rational and irrational. So a rational number, remember, is a fraction. So I'm going to put a definition down just to kind of motivate what we're about to do. So I'm going to do P over Q, just like that. Okay, so a fraction looks like this. That's a rational number, but strictly speaking, we're going to exclude Q from being 0. Okay, and of course, P and Q are going to be integers. Okay, so that's our definition of a rational number. Right, let's set up the start of the proof then. So we're going to assume that A is rational and non-zero. Okay, so what does that mean? What can we write down based on that? Well, we've got a definition here. If it's rational, we can write it as a form like this. So I'm going to use P over Q for this. Okay, but we've got Q not equaling 0 because we can't divide by 0, but also we can also say that P is not 0 either because we're assuming here that A is not 0, so P isn't 0 either. P, Q are integers. I'm writing it using set notation, and then they're also not equal to 0. Great. Okay, what else are we assuming? We're also assuming that B is irrational. I'll put assume as well, because we're assuming it. Okay, so there's no real way to write down an irrational number in a particular form, right? All we're saying is that it's not of this form here where we can write it as a fraction. So I'm going to leave it as that. Okay, but we're also then going to assume that AB plus 1 is not irrational. Okay, we're negating our conclusion here. So if AB plus 1 is rational, that means that we can write it in a form like this that shows it's a fraction. So we've got AB plus 1 is, and I'm going to use different numbers, different letters here, M over N I'm going to use. Okay, now this could be 0 if I wanted it to be, but all I'm showing is that N is not 0. That's my only assumption on this fraction here. Okay, but then M has to be an integer, and N as well. Okay, right, so our setup is pretty much complete now, right? That means everything that we're assuming here is written down. Right, let's do some kind of logical steps here. So I think what we should do now is replace A with my P over Q, and then our aim is to then get a contradiction here, and our contradiction will be to do with the fact that B is irrational here. So let's do that first of all. So let's replace A. So we've got P over Q times B plus 1 equals M over N. Okay, and now I'm going to solve this for B. So I'm firstly going to subtract 1. And I'm also going to put B on top with P there. So PB over Q plus 1. Sorry, I'm going to take away 1, aren't I? Okay, so that equals M over N minus 1. And what I can do here is I can combine this into a single rational number using a common denominator. So this is going to be M minus and then N on top and then N on the bottom like that. Okay, now I'm going to quickly solve for B. So B is P lots of this M minus N. And on the bottom, I'm going to divide by, sorry, I've got that wrong, haven't I? Sorry, this is meant to be Q on the top because Q was on the bottom over there. Q goes there. P comes underneath, so now we've got this. Okay, great. So we've rearranged and we've shown B in this form over here. Okay, so now we're pretty much done because look at what we've got. We've got These numbers on top, doesn't particularly matter what they are, but we know that this is going to be an integer. The numerator is an integer. And on the bottom here, we've got p. But if you look at what we wrote when we wrote down a as a rational number, p can't be 0 because a is not 0. Okay, so what we've done is we've written b as a fraction, as a ratio, so b is rational. Okay, but that contradicts what we've written here because we assumed that b was irrational. So our proof's done. And then to finish it off, I'm going to put this down here. Okay, so we're finished now because of this contradiction, our assumption that the conclusion was false is itself false. So we've proved the statement as a whole. Okay, great. Okay, number 3, this is a different type of question, and it is another one that is quite frequently appearing in past paper exams, and it's to do with finding integer solutions to equations. So there's a reasonably simple equation here that we want to solve over positive integers, but we want to actually prove that it's got no positive integer solutions. So the idea here is the same. We don't really have a hypothesis conclusion structure here. This isn't really a P implies Q question here. But if we assume that this is a false statement, we can then get some contradiction that we know is definitely false, right? So sometimes the contradiction will be something to do with what's in the question, but on other occasions it will be something like arriving at 1 equals 2, or showing that an odd number is equal to an even number, that kind of thing. Okay, so let's prove this third one. If you want to have a go before me, then have a go. Okay, so our assumption step, we're going to assume that this does in fact have a positive integer solutions. Okay, so we are kind of imagining that there are some numbers x and y, which are positive integers, that satisfies the equation. And then we're going to see what we can do with this equation here. Okay, so I'm going to write this out again so I can do some manipulation. Now, what I've got here is I've got a kind of addition problem here. This addition on this side makes it quite difficult to solve, particularly when you've got integers, because adding integers, there's lots of ways to do that. But multiplication is a much more powerful way, particularly if I can get something factored. If I can factor something, then it's a lot easier to show what integers I'm allowed to have in terms of what's adding together. So I'm going to subtract y squared onto this side. Okay, I've spotted that I've got 2 squares here. If I subtract them, then I can do some factoring because that's the difference of 2 squares. So now I'm going to factorize this. Okay, so that's factored. But now, seeing as we're dealing with integers, I have only a few different options as to what these brackets could possibly be. And that's going to be this. So either x plus y is 1 and x minus y is 1. Okay, bear in mind these brackets are integers, that's the only thing that it could be. Or they could possibly both be negative 1. So let's write that as well. Okay, so these are the 2 cases that we've kind of broken this down into. And we're going to show that in each case we get something contradictory. So in this first example, let's add together, and then let's try and solve for x and y. So I'm going to add these equations, and that's going to give me 2x equals 2, and then that means that x equals 1. But then that means that if I stick back into the first equation, that's going to mean that 1 plus y equals 1, according to this line, but then y equals 0. But y is 0 is a contradiction because we assumed that x and y were positive integers. Okay, so that case hasn't worked. Great. Okay, in the second example, we should get something very, very similar for our contradiction. So let's add these together as well. So if I add these up, then I get 2x equals minus 2, x equals minus 1, but again, that's not positive. Okay, so we get a contradiction in both cases. Excellent. Okay, so that's done. So my main advice here is to think about the fact that you've actually got integers for your values, because that gives you a lot more methods to play with. If you can factor something, then the fact that these things are integers splits it into only a few different cases. Great. Okay, let's have a look at some more examples. I've got a few more. So fourth example. This one's a slightly more difficult example compared to the previous, but it's based on the same kind of idea. So we're proving that a squared minus 4b equals 2 has no integer solutions. And this time by integer, we're talking about positive, negative, and 0 if possible as well. Okay, so let's have a go at this. So I'm going to prove. We're going to assume that this does have integer solutions. Good. Again, this means that they're integers. I'm now going to do another factoring trick. I'm going to add 4b to the right-hand side. Okay, and then by doing that, I can then factor out a factor of 2 on that right-hand side. Great. Okay, so then because I've taken out a factor of 2, what I've done is I've shown that a squared is even. That's because it's a multiple of 2. Okay, so if a squared is even, because of the 2 that's here, I can then rewrite a as even as well. Bear in mind, if a squared is even, that means that a is also even. Okay, we proved that in example 1, in fact. So go back and have a look if you don't believe me. A is even, that means that a is 2 times, let's call it c, because I haven't used c yet. So then if I were to plug 2c back into my equation, let's do that. I'm going to put it back in here. So then that means that 2c all squared equals 2 times 2b plus 1. And then that means that 4c squared equals 4b plus 2. Okay, now what I'm going to do is I'm going to divide by 2. 2c squared is 2b plus 1. Okay, right, now we can get to a point where we're talking about a contradiction. Because on the left-hand side, we've got a multiple of 2, and multiples of 2 are, by definition, even. But then on the right-hand side, we've got a multiple of 2 plus 1, and that's going to make this right-hand side an odd number. Okay, but then these two things can't be equal because an even number can't equal an odd number. So that's going to be our contradiction. Okay, all right, so hopefully you followed along with those steps. It's a little bit trickier than you might expect in an exam, but it's a nice one that I think is worth seeing, just to see kind of how these things kind of follow with their steps. Okay, let's move on to some much more famous examples, I think, now. Okay, so proving that root 2 is irrational. I do believe you've seen this before, but if you can't remember, it's worth you getting these steps down. You never know when it might appear. So, boys and girls have learnt this for thousands of years. This is very, very old proof from antiquity. So, proving that root 2 is irrational. So, our initial assumption, as always, is that this is a false statement. So we're going to assume that root 2 is in fact rational. And we know how to write a rational number down. We can write it as a over b, whatever letters you want to pick. And then a and b are integers. B is not 0. Okay. And also, because we've got a fraction here, we may as well assume that a over b is written in its simplest form. If there are any common factors between a and b, we might as well cancel them out to make sure that this is in its simplest form. Okay, there's nothing wrong with assuming that. If we've got a fraction, then we might as well put it in its simplest form and then continue. Okay, now we're going to play about with this and see what we can do with it to derive a contradiction. So I'm going to firstly square both sides. So if I square both sides, I get 2 equals a squared over b squared. And then to clear denominators, I'm going to times by b squared. So 2b squared equals a squared. Okay, now we're going to continue similarly to how we did the previous example there. So this 2 here is showing that a squared is even because it's a multiple of 2. But then we know that if a square is even, then the thing that got squared is even, so a is even. That means that a is 2 times c, which means I can then feed it back into the equation. So then I've got 2b squared equals 2c all squared. Now I can write 2b squared equals 4c squared. We can then divide both sides by 2 on both sides, so b squared equals 2c squared. And then we can play the exact same trick again. I've written b squared as a multiple of 2. That then means that b squared is even. But that means that b is even. Okay, and now I don't need to continue because I've arrived at my contradiction if you look carefully. So what we've now shown is that first of all, a is even, that's over there. And then we've now shown that b is also even. But then you'll notice that that contradicts our assumption over here, which was that we got this fraction in its simplest form. Okay, so our contradiction is has been reached. Okay, so we basically discovered a fraction that can't be put in its simplest form, and that's a contradiction. Okay, and because of the contradiction, that means that root 2 must be an irrational number. Okay, right, that's a very famous proof. It is worth you knowing that one off by heart, I would think. If you want an extra challenge, there's a little extension to this that I can think of that you might want to have a go at. So to extend yourself, have a go at this. Prove that the square root of p is irrational. So I'm going to generalize this to the square root of p, where p is a prime. Okay, you can probably get about halfway or 2/3 of the way through by following the same steps. But there's a little extra thing to consider that you might want to maybe look up if you're not quite sure. Otherwise, have a good go, and I'll be impressed if you can get right to the end. Fab. Okay, right, a couple more to have a look at. Exercise 6, number 6. So this is another famous example. We're proving that there are infinitely many primes. Okay, it's something that you hopefully already believe, but it's easy to kind of maybe imagine that the primes suddenly run out. They certainly get thinner and thinner and thinner, and they get more and more sparse the higher you climb, but there are in fact an infinite amount, and we're going to prove it. Okay, before the proof though, it might be worth thinking about the proof with a small kind of numerical example, and that's going to kind of help us understand the proof. So let's, before we do the full proof, let's suppose that 2 and 3 and 5 are the only primes. Okay, we know that there's more than that, but let's suppose that these are the only ones that we've ever found, so these are the only primes that exist. Okay, so that means that this is a full list, a complete list of primes. Okay, so now what I'm going to do is I'm going to take my prime list and I'm going to create a new number using those, and that's going to be called capital N. Okay, that's kind of the tradition as to what you use for this big number. So this is going to be 2 times 3 times 5 times together, and then I'm going to add 1 to that. Okay, now that is going to be 31, but it's not that important that we know what number it is. We just know that we're timesing all the primes that exist together, and then we're adding 1. Okay, well, firstly, if there's two possibilities of what kind of number n can be. So firstly, n could be a prime number, but if you think about what we've got here, this is a complete list of primes. So my bigger number here can't possibly be prime because it's bigger than 2, 3, and 5. So that would be a contradiction. Okay, so if it's not prime, then that's our second case. Okay, so we've exhausted the case where n is prime. That can't happen. If n is not prime, then that means that it must have some factor that's other than 1 in itself. So in particular, it's got a prime factor. Okay, so n has got a prime factor, and our only choice of primes belongs to this complete list, 2, 3, and 5. But the way that we constructed the number means that it's not going to have any of those as factors, because there's always going to be a remainder of 1 when you try and divide into that number. Okay, so that's another contradiction. So in each case, we can't have either of those, but n has to be prime or not prime, so we're done. So this number can't really exist, if you like. Okay, so that's the kind of idea behind the proof, but obviously there are more primes than 2, 3, and 5, so we're going to have to generalize this to a kind of arbitrarily long list of primes. Okay, so the proof goes like this. In fact, I'm going to clear these annotations so I've got more space to finish off. Great, okay. So let's do the full proof properly. Okay, so our initial assumption is that actually there is a list of primes that's finite. Okay, so let's make a complete list of these. So I'm going to use some algebra now to denote all the list of primes here. So I've got prime number 1, prime number 2, prime number 3, and that's going to continue. And then there might be a big long list, but the final one I'm going to write as P sub n, like that. Okay, bearing in mind as well, this is supposed to be a complete list of all the primes that exist. Okay, and obviously I can do that because my list is finite, so I can write them all down. Now we're going to consider this big capital N, which is the product of all of these primes. This is timesing together now rather than listing. And then we're going to add 1. So case 1 is that N is prime. But that obviously can't happen because it's bigger than all of these individual primes, and these primes make a full list of all the primes. So I'm going to write n is bigger than p1, it's bigger than p2, and it's bigger than all of them. So all of them look like that. Okay, case 2 then is that n is not prime or composite. So that means that n has a prime factor. And because the prime factors belong to this list, I'm going to call it pi. So this is one of the primes that we know has to be a factor of this n. But that can't happen as well because pi, one of these primes, whichever one, won't divide into n because it leaves remainder 1. Okay, so that's our contradiction. Great. So it's like we've been kind of chased down a narrowing corridor here, right? As you go through the cases, we find that none of them can happen, and then finally, the final blow to our argument is down here. Great. So that's proved, and that goes back to ancient Greece. Fantastic. Okay, right, I've got one more example and then our video is done. Thank you very much for persevering with this difficult topic. Okay, so one for you to maybe have a go at. If you want to pause the video and have a go, this is reasonably difficult. But if you know how to get started, chances are you can get quite a way through if you persevere. So best of luck, and in a second I'll give you the solution. Okay, so let's prove our final example using proof by contradiction for the final time. So if you think about this sentence, we're proving that every positive integer is a product of prime numbers. Okay, now in fact we can make a stronger statement and say that this is a unique product of prime numbers, okay, which is a very, very important theory in mathematics. But for now we're just proving that it is some product of prime numbers. Right, our assumption then is that this is false. So let's start the proof. We're going to assume that there are some numbers, at least, that are not products of prime numbers. Okay, and notice how I've negated this. So we're showing that to negate the fact that every integer has this property, we've got to assume that there is at least one that does not. Okay, not that none of them do, that there is at least one that doesn't have this property, and then that's negated. Okay, so if some numbers can't be written as products of primes, then there must be a smallest one. If we're talking about positive integers, then there must be a smallest one. So let's let capital N, my favourite letter for today, be the smallest of these. Okay, so let's think about this. This is the smallest number, or smallest positive integer that's not a product of primes. Okay, so what can we say about N? Well, we can say something similar to what we had for our previous proof. Let's think about whether or not N is prime or not. So could N be prime itself? Well, it can't, can it? Because if N is prime itself, then it is a product of primes because it's just itself, and that's a product of primes. Okay, so it'd be a product of primes, and that prime is itself. Okay, so that's out. We can't have n being prime. So that means then that n is not prime. Okay, so then if n is not prime, that means that it's got factors, both of which are smaller than n. So I can write a and b. A and b are the factors of n, but crucially, they're both smaller than n. Okay, if you think about a composite number like 10, you can find two factors, 2 and 5, that are both smaller than that number 10. Okay, so now let's think about what we can say about a and b. Well, a and b are smaller than n, and n is the first number you get to that doesn't have this property of being a product of primes. So that means that a and b themselves must be products of primes, okay? Because they are not big enough to be in this list up here. Okay, so that's because of this. So if I can write a and b as products of primes, then let's do that quickly. It's P1, P2, P3, up to P, let's call it PR. And then B is another product of primes, let's call it Q1, Q2, Q3, up to QS. So these are the primes that make up A, these are the primes that make up B. If I were to then times them all together, I get a long list of primes. Okay, so look at this. I've got all the p primes here. I've got all the q primes here. But as a big long list, this is a big long product of primes. But we're done because then that contradicts this statement here that says that n cannot be written as a product of primes. Okay, and that one's finished. Right, I think that's all the examples that I can possibly think of in the world. I'm done with doing these now. Hopefully you've learned a lot from these videos and that you've started to memorize some of the more classic examples. And hopefully if you see one in an exam, you'll be able to blitz it. All right, thanks year 13. Thanks for sticking with me. Enjoy your day.